is actually atrial fibrillation. It's to some extent seen as the one that is clinically significant. Sometimes if it's not detected and attended to, it could lead to stroke and to death. And so this doesn't mean that it's the only one, but it's the common one. And there are others that affect human beings differently, but this has been seen to be the really significant cardiac arrhythmia. And so to diagnose arrhythmias, we use the electrocardiogram, which people commonly call the ECG. And for atrial fibrillation, if you look at the electrocardiogram and it has an absent P wave replaced by maybe fibrillatory waves or oscillations, then that is indicative of a case where atrial fibrillation is present. So in this slide, I just show a little bit of what an ECG looks like. So if you consider this as your ECG, and usually this is what a normal ECG looks like. So these are 2 heartbeats, okay? Two normal heartbeats. What you see here is what we call the P wave. And then here we have a QRS complex. And then here we have what we call a T wave. So this keeps repeating, and that would be registered as a single heartbeat. So between 2 R peaks of 2 heartbeats, we have what we call an RR interval, which is also one of the features that is commonly studied by people who are studying the ECG. So what the R peak represents is the maximum amplitude of your heartbeat, or in this case of what the normal heartbeat would be. So in a case whereby this part here is missing, which is the P wave, that means that the person probably has atrial fibrillation. And so this is what we have, in this work, this is what we have been trying to do, checking if a P wave is present or absent, detecting if atrial fibrillation is present or absent, and then trying to explain that using expert knowledge. So our approach mainly focused on an intelligent agent for arrhythmia diagnosis. And we came up with what we call a personal health agent, and it combines a machine learning component for ECG pattern detection, and then it also has a Bayesian network for capturing causal knowledge and providing plausible explanations. So I'll just start by telling you exactly what the PHA architecture or the personal health agent architecture looks like. So what we had for our agent was an external AI service. We actually called it an AI service because most of the literature on agent programming in the machine learning era calls it an AI service, whereby the machine learning is used in relation to the agent to achieve some tasks. But we actually thought maybe it should have been called an ML service because, I mean, the rest of the agent is also incorporating other AI techniques, and so the AI service would be a mixed name at that point. But yes, we tried to maintain that terminology because that's what the agent community was using. And so the agent had the initial architecture of the agent. The agent had an AI service in which we had a model building phase, and then we used that model to detect a pattern, in this case whether P waves were present or absent, and then whatever comes out of that is what was used as a percept to the agent. And the agent had has two endogenous modules. One is perception and the other is deliberation. And so in the perception part, we had a case where we were detecting what pattern what situation that pattern is indicative of, maybe atrial fibrillation or not. And then in the last part of the architecture, which was the deliberation module, we are trying to explain the occurrence of the situation that we have seen. So in the next few slides, I'm just going to talk about what exactly happened in each of these modules of the agent, and of course, how they were interacting with each other. So to provide some detail on the data set that we used, of course, we had to train a machine learning model that classifies an ECG signal based on whether a Pwave is present or if a Pwave is absent. And so we had a data set that we obtained by combining two databases. The first database was the AFDB, atrial fibrillation database. And then the second database was the Pwave database. So the Pwave database gave us the negatives, and then the AFDB actually was used for us to obtain the positive class. I hope I remember that correctly. I could have interchanged it. So the AFDB database had 25 records, but 2 of them were incomplete. So we only had 23. Those are the ones that register, and then the other one had 12 records. And then what we did was that we randomly selected 12 records from here so that we can have a balanced data set, and also we separated the channels, or you can call them leads for those that do a lot of ECG. So the channels come from different parts of the body, or the leads come from different parts of the body. I'll not go into the details of where exactly those parts of the body is, but they could be in the limbs or whatever. So what we did was we made sure that we had a balanced data set, and we also resampled so that we can have the same frequency for the two databases, or for all the records. Maybe something else that I can say, we for each of the channels, we made sure that the R peaks in each of the signals was identified, and then we segmented the signals into heartbeats using the R peaks, and then we removed the last and the first so that we can only consider the ones in the middle, because we are looking for the strong heartbeats. And then we made sure that at the end of the day, we had 24 records from each of the data sets, 12 from each, and then we ended up having about 53,000 bits at the end of the day. So for model building and pattern detection, we had 4 machine learning classification algorithms that were implemented. We had the MLP, the logistic regression, support vector machines, and random forest. Trained using tenfold cross-validation. So we obtained the average accuracy, the average F1 score, and also a summed up confusion matrix. And so from our findings, based on that the data set that we used that I've described in the previous slide, we had MLP being the best performing model. And we also compared it with what was in literature, and it was actually still performing better than the support vector machine. And so now the MLP being the best performing model is what we used as the model that we are going to incorporate in the AI service to detect the presence or absence of the Pwave. And so if that percept is given to the agent or to the endogenous parts of the agent, the next part is now to determine what situation that is indicative of. And since we had just 2 steps, which are presence of Pwave or absence of Pwave, we decided that we can actually do the situation detection using the Bayesian network itself. I'll explain more about the Bayesian network in a slide or 2 to come. So for situation detection, what we are doing is determining again what the pattern indicates in reality, and whatever it indicates is what we are calling the external semantic interpretation. So in this case, the interpretation would be AF or absence of AF, depending on whether it's a Pwave that has been seen to be present or absent. So to detect the situation, we obtain the pattern and capture the pattern in the Bayesian network. And then the situation that this pattern represents is determining by propagating probabilities. And I'm going to explain exactly how this works when I flash the Bayesian network. And then, of course, the situation has to be checked whether we are going to follow it up or there is nothing to follow up. And by following up here, we mean explaining exactly what the underlying causes might be. So the last module is the deliberation module. And this module involves trying to explain, like I said, the presence of AF in an individual. And for the explanations, we were using the traditional risk factors that have the highest conditional probabilities. I'll explain a little more of this. But this was done using the Bayesian network, and to design the Bayesian network, we used expert knowledge. And also the Bayesian network was evaluated using Pitchforth and Mengersen's framework. So for Pitchforth and Mengersen's framework, there are a number of aspects that are evaluated for the designed or expert elicited Bayesian networks. But in this talk, I only focus on one, which is predictive validity. But actually, there are other aspects that we wrote up in the paper, but I do not talk so much about in this talk. So the first instance, or in the first instance of the PHA, this is what the Bayesian networks looks like. So if maybe you're new to this concept of Bayesian networks, a Bayesian network is just a direct acyclic graph. So in other words, in our network, we are not going to have any loops in the network because it's a DAG. And then it consists of nodes, and then it consists of arcs. So in the network, whatever you see as an arc represents some sort of influence. Usually people who work with Bayesian networks maybe focus more on causal influence. But yes, it represents some sort of influence between the nodes that are connected by the arc. Now, for each node that we have in the network, we have conditional probability tables for each of those nodes. So underlying each of the nodes, actually what is seen here is a representation of that comes from the conditional probability tables that are designed for each of these nodes. So for a node that does not have a parent, that means we shall only have the prior probabilities. But if a node has a parent, then the probabilities will be influenced by the parent node, and that's why they're called conditional probabilities. So in a case where we have evidence, and by evidence we mean now we know that something is 100%, we are 100% certain that something has occurred. In that case, we would say, okay, put the evidence in the network. And for example, if we have seen that a Pwave is absent, the Pwave node will have 100% absent here. And then those probabilities will be propagated. So now we would know the chances of someone having atrial fibrillation, given that we have seen that the Pwave node is present. And then we could know the chances of these other risk factors. So in the representation of the Bayesian network that we have, the way it's designed is based on how schematic BNs for medical BNs are designed. And so whatever you see as RF, that represents a risk factor. And then what you see as C, that represents a condition. This node is what is used to interface between the Bayesian network and the machine learning, because this is where we capture whether a Pwave is present or not. And so in this case, we still have what we call context nodes. For example, age and sex, those are demographic context nodes. And then we have some lifestyle risk factors here. For example, alcohol abuse, smoking, and obesity. Those are considered as lifestyle risk factors. And so if any of these, if we have information about any of these, in addition to knowing what has been returned in the pattern detection phase, then we can add information about this as evidence, and then we can actually see exactly how these other nodes for the risk factors behave in a way that is going to explain how, why a person has atrial fibrillation. So this is what the network looked like, and this is what is in the agent's head, and it's what is used for deliberation, just to explain what is happening. So maybe something else that I need to say is that the likelihood values for this node are probability estimates that are obtained from the machine learning using this method. So from what you've seen in the architecture of the agent, most of what is happening in the agent is done using a Bayesian network. And so to evaluate that, we have to look for ways to evaluate the Bayesian network. And so we drew from Pitchforth and Mengersen's framework. And one of the aspects that we needed to evaluate was predictive validity. And so we went ahead and looked at what is said in literature, in medical literature, about most of the things that we were introducing in our network and how our network was behaving when it was executed. And so we are not considering the Pwave node at this point, but we're just considering a case where atrial fibrillation is actually 100% present. And so in this case, if AF is present, we're seeing the behavior of the rest of the nodes, and we are able to compare those with what other values are saying in literature. But because of population issues, different populations respond differently. So depending on the population that you're working with, your figures have to fit through a certain range. And so we compared with Nguyen's work, and we were looking at what the network was saying and what Nguyen was saying for the minimum and maximum values. And then, so actually predictive validity has three things that have to be measured. The first one being how the BN behaves when it is executed. And then the second thing is sensitivity to findings, and there are specific measures for sensitivity to for analyzing sensitivity to findings, and that is entropy and mutual information. And so we were able to calculate this and see exactly how our BN is working. And so what we have here, you can concentrate on the first column, and maybe I'll go into the second a bit. We don't use a lot of variance of beliefs, but it's also a measure of sensitivity, and we actually work that out. But our interests are here because this is what we apply later. And so to measure the sensitivity to findings, like I said earlier, you can use entropy. And so we are able to see how much information if we know any of these nodes, how much information we can get about atrial fibrillation. And so, for example, Pwave, the Pwave will give us some information, probably more compared to alcohol abuse and the like. And then the third thing about looking at predictive validity, is actually modeling extreme conditions. And so we have some extreme conditions, especially when it comes to atrial fibrillation. Of course, the chief indicator is that the Pwave has to be absent. But then, based on medical literature, males are susceptible to atrial fibrillation more than women. And also older people may get atrial fibrillation more than younger people. So that's one of the extreme conditions that we modeled, and we were able to actually check out how the rest of the Bayesian network behaves based on those extreme conditions. So you're able to see that maybe chances are not so high, just about 50% that someone might have hypertension. But when you increase the extreme conditions and make it a male old man who has a Pwave that is absent, and they also have these lifestyle risk factors, the chances of hypertension increase, but also we are seeing that the person actually, the chances of ischemic heart disease also increase. So those are the three ways that we check the predictive validity of what we have decided, in this case, a Bayesian network that we have decided to put in our agent. And so we went ahead to improve this work, because this was actually, at this point, this was an invited extension of this work. So to extend the work, we actually used a larger data set. Instead of binary classification, we also opted for multi-classification. So it is not just atrial fibrillation present or absent, but it is atrial fibrillation, other arrhythmia, or actually the person is normal, so there is no arrhythmia. And then in our training, we also added some demographic features because they were in the new data set that we used, and they improved actually what we saw. And then we also had to improve the Bayesian network, definitely, because now at the point of the arrhythmia node, which initially was just atrial fibrillation, we needed to have some 3 nodes there, and they were representing atrial fibrillation, other arrhythmia, and then no arrhythmia at all. And then an important module that we added was this decision support module, which now is forming the interface between the user and then the rest of the agent. I'll explain more about what is happening in the decision support module and how it draws from the findings of the Bayesian network. And then we also changed the interaction between the Bayesian network and, like I said, we moved, maybe I didn't say this, we moved the machine learning model to be part of the agent, and so it's no longer exogenous to the agent. And then we added this module and also changed how now the Bayesian network and the machine learning module were interacting. And then, yeah, I think those are mainly the changes that we made to the PHA in the extension of that paper. And so, like I said, we had these two demographics, in addition to the statistical features, and the statistical features that we used were mainly mean, standard deviation, variance, kurtosis, what else? Skewness, and maybe one that I've forgotten. And we did those, we obtained those statistical features for RR intervals that I described earlier in the ECG, and also for the R peaks. And then we also obtained the root mean square for each of the channels, each of the leads. That resulted in about 12 features, plus the other features that come from the statistical features, and then including age and sex. I think we ended up with about 160 features, 150 something maybe. Yeah, so for our records, this is how the records look per class. We did both multi-class and binary class. Multi-classification and binary classification. And so also, instead of doing logistic regression, we did gradient boosting, random forest, MLP, and SVM. And this is how the results looked when we did the binary classification. We had an accuracy of 93.85. And then this is what the confusion matrix looked like. And for each of the classes is what the rest of the evaluation matrix look like for each of the algorithms that were implemented. And then when you move on to the multi-class, of course, it's lower, but it was still, gradient boosting was still the best with 82.88%. and this is what the rest of the matrix returned. And so because gradient boosting was the best at this point, we actually implemented gradient boosting. So it was no longer MLP, it was gradient boosting, and that's what we implemented for pattern detection. The Bayesian network is almost the same. It's just that we had to improve our machine learning interface node so that we have 3 classes. And definitely also now the arrhythmia node, which represents the condition, also had 3 classes that train with each of these. And then we added 1 extra node because now at that point, most of the literature had added that this was raising a lot of arrhythmia issues. And so we added that too, but the rest of the network behaves the same way. For the interaction between the machine learning and the Bayesian network, the first thing is how did we obtain the conditional probability table for this node? And so the conditional probability table for this node comes from what we had here. So we use the recall values. For example, if we have, or maybe you could actually say there's actually the same values with what we have here, but we use the recall values. And so for us, this is what the conditional probability table for that specific node looks like, for the interface node. And you realize that these values actually match with what we had in the machine learning. And the backing for why we use the recall values is that what you're looking for is, okay, the machine learning is saying that this person has atrial fibrillation, but we have to cater for the negative, for the false negatives and false positives. So in that case, what this is saying is that it's only up to 89.1 chances that a person indeed has atrial fibrillation if the pattern recognition submodule has said that the person has atrial fibrillation. So it's not exactly 100%. And likewise for the rest of the nodes, since we can't say the machine learning component is 100% accurate, that means even what we have in our Bayesian network has to rhyme what we are receiving from the machine learning. So that is why we use the recall values to obtain the conditional probabilities. And then for sensitivity, I now skip some of the things that I've already talked about before and just move on to what I haven't talked about for the PHA. So for the sensitivity to findings, at this point now, we are looking for information. How exactly are the rest of the nodes adding information to our beliefs or our certainty in the fact that someone has arrhythmia? So in this case, of course, the machine learning prediction node, the one that you saw here, this one, gives us the most information about the presence or absence of arrhythmia, followed by the rest of the nodes. And of course, this one gives us the least information. So you can't go and say because someone is drinking alcohol, they have arrhythmia, because there is very little information that adds. But then if you put it together with other risk factors, then actually arrhythmia increases. And so I'll take the next maybe about 5 minutes and discuss the decision support module, which we introduced in the extension. And so with the decision support module, we are providing 2 kinds of decision support to the user, and that is predictive decision support and diagnostic decision support. And predictive decision support is mainly focused on finding out, maybe the user wants to find out the most relevant information that might increase their certainty about the presence of arrhythmia. And then for diagnostic support, you probably know that the person has arrhythmia and you're trying to find out what the underlying cause might actually be for the presence of that arrhythmia, given the context nodes like the demographic features, maybe some lifestyle nodes like alcohol abuse and things like that, and any other information that we have about the individual. And so what I have here was done using Autonetica, and what exactly is happening is we are implementing the values that we have for mutual information. So these are the values that we use to give the user predictive decision support. And if they do not know the answer to any of these conditions or risk factors, then they can just skip that and add information. But as they add information, the agent actually helps them to improve their beliefs on whether a person has arrhythmia or not. So what happens is that if you have an answer to any of these, then your beliefs in whether arrhythmia or atrial fibrillation in this case is present or not will keep increasing based on that, or on the information that you have provided. So that's how the agent is offering predictive support. And like I said, the underlying technique at this point is the use of mutual information for us to be able to determine that. Most of this was done using the Java version of Netica, which is Netica J. So even here, what is happening is we know that the person has atrial fibrillation, maybe they're 85 years old and have some lifestyle risk factors. And so we want to know what underlying condition or risk factor they might have that might lead us to an explanation of why they're having atrial fibrillation. And in that case, this doesn't exactly mean that the person has hypertension, but this means that maybe this is something that should be followed up or checked to make sure it's not the reason someone is having atrial fibrillation. And likewise, this could say, just check if there is some ischemic heart disease, but doesn't exactly mean that the person has ischemic heart disease. So this just provides some risk factors that can be followed up. So this is what we're calling diagnostic decision support, and this is what we're calling the predictive decision support that is provided to the user. And so in conclusion, what I have demonstrated is how we did a combination of data-driven techniques and expert elicited knowledge so that we have a hybrid approach for decision support and diagnosis of arrhythmia. To be honest, we could not find any publicly available data set for wearables, like data coming from wearables like your normal Fitbit or whatever, maybe a smartphone. So we trained using a 12-lead data set. And so for this to become better, we would have to train using data that has come from wearables, because at the end of the day, the incoming data would actually have to come from wearables and not a 12-lead, something that is placed all over the chest and the arms and the limbs and whatever. And then lastly, like I said, we did Pitchforth and Mengersen's framework for evaluation. But actually, we also did informal evaluation with the medical person, but we do not report about that. But we say that actually maybe that would be an important thing to do, especially now that this is an expert elicited Bayesian network. It would call for co-designing maybe the network with the expert, or at least have some rigorous evaluation by the expert before it is added to the PHA. But the aim was to prove the concept, and I think that's what we achieved. So these are the two papers that I have quickly been talking about. Yeah, we had one that we published in 2022, and then we had now to do the work for the invited extension and completed it last year, and it was also published. Thank you. Oh, I just need to acknowledge that I didn't do this alone. I worked with Mbithe and also with Catherine Sue Price, and definitely with Professor Modley. Thank you.
Right. Thank you so much. Hey, there is echo. Actually, it's better.
Sorry?
Good. All right. So thank you so much, Tezira. And I want to open up for questions. Any question? Yes, Dr. Joseph, please go ahead.
Hello.
Hello.
Yeah, thank you very much. It's a very good presentation. I think in terms of real life application is quite good. I didn't understand a few things. Maybe you could have dealt with this kind of data before. In terms of when you are at the machine learning part, what kind of features were you extracting? Like because you showed, I think there were 23 and then 12 participants. I didn't understand how it came to those thousands of samples, and then what kind of features were you extracting to feed into the machine learning model?
Okay, so I'll just point to the improved part. So specifically for the improved part, the dataset had two demographic features, which was age and sex that we used. But then we also obtained some statistical features that we used, which were mean, median, standard deviation, variance, kurtosis, and skewness. And then, so we obtained those statistical features for the RR interval and also for the R peak for each of the 12 channels, for each of the 12 leads. So that gave us, I think, about 144 because we had 12 leads and then we had those 6 features and we were doing for each of the leads. And then we also added the root mean square, the root mean square for each lead, which gave us, I think, about 12 features. So in total, we had about 158 features that we used.
In the statistical features, did you get any problem with the variance between different people, like participant 1, in a case where it was positive, the same value in participant, let's say 3 is, did you get any, and maybe how did you deal with the variance between persons?
So we did not actually do that. I don't remember exactly at this point, but we did not look at each of the patients at that point for their individual variance between the two.
Mm-hmm. Okay, thank you. I will look at the paper more, and then it will be nice.
Thank you so much, Dr. Joseph.
All right. Any other question? Yes, Gilman.
Thanks, Tezire, for the presentation. Great work. Probably not a question, but if you are considering next steps, a few things you could check is, one, the data you mentioned, it is 12 lead ECG, right? And how do you combine these different channels is a key design choice, as it could, follow up different data.
Sorry, say that again. I might have missed something.
All right. So the 12 lead ECG you mentioned, it could be integrated in different form, and one thing you could analyze is what would be the best way to fuse different channels. Do you really need to use all the 12 leads, or should you just focus a few ones, which will definitely reduce the computational impact and so on. That's one thing. Two, when you present the results, and I wonder if you checked the error. Usually understanding where things go right is a good thing, but at the same time, for which kind of waves and data components your model is making an error. That sort of analysis also gives you where things are going and how potentially you could improve the performance of your model. The third component is ECG is quite expensive to collect, right? Usually you need those electrocardiogram, mounted on the chest, often at 12 places. So an alternative research area is to use cheaper wearable sensors and signals like PPG, for example. You could just put in on your finger and you could collect data quite easily. So if you check across these three different topics, that would be great.
Thank you so much. That is really, really wonderful. Thank you.
All right. Anyone else or someone else with a comment or a question for Tezera? Okay then, thank you so much for taking time and making time to attend the presentation today. I will then say we call it a day and see you next month. The notification will come as usual, about 2 weeks notice. So thank you so much and enjoy the rest of the afternoon. And thank you so much, Tezera, for making time to, talk to us about the work that you've been doing, and looking forward, as we discussed earlier, to further collaborations and partnerships with Microsoft team researcher in Nairobi. So asante sana and enjoy the afternoon too.
Thank you. Thank you everyone for coming. Bye.
All right. Yeah, bye.
Bye-bye. Thank you.